We talked a lot about operating expenses, capital expenditure. We look into detail how we estimate capex, equipment costs, procurement costs, construction costs, we calculate OPEX. For this we already saw many times. For example, if cost of natural gas is 30 euro per megawatt hour, how we calculate based on LHV efficiency, what will be the power price. And then in the morning session also we talked about we cannot simply add capex and OPEX, how we estimate total cost of ownership from capital expenditure and operating expenditure. So basically, in very simple terms, product price or product cost will be cost incurred, whatever cost we and whatever profit we are targeting. Right? So let's continue to take this simple example, what we have been doing for last 2-3 days. CO plus hydrogen that goes to methanol. That's how it looks like in a laboratory. In real plant, it will look like differently. So we have the reactant A and B coming in, product coming out, and we have cooling water outside the reactor in the jacket to keep the temperature under control. Right? So just looking at this figure, what are the costs we can see? The raw material, you need to buy your raw material, right? You need to pay for cooling water to dissipate heat. You need electricity to run the pump, compressor, whatever. So these are gases, you compress it at high pressure. So compressor for your feed, pump for your cooling water. So electricity for many other things, lighting the plant, all this alarm system, all these control walls. So then you need to buy all this equipment, right? But what we sometimes forget, there's a lot of money involved in, you need to insure your plant. If something happens, you don't want to shut the shop. So somehow you want to keep it insured. So salaries, interest payment, you will buy this equipment probably from your pocket, or you will take a loan or credit. So you have to pay interest on this. Right? So let's categorize the total costs before and after production. Before production means once you start production, all the costs what you have to pay before it, and the one after it. So basically for your capex, so buying your equipment, installing it, once you bought it, but you also have to install it. So a lot of civil work, a lot of cost incurred here. Buildings, control rooms, all kind of buildings. You have to pay for contractors to perform these tasks, because you cannot do everything. And there are many other costs, and we'll see probably later. Once you start production, what you pay is for your raw material, electricity bill in simple terms. You generate some wastewater, so you have to treat it. So insurance premium, if it's a special process and you bought it from some licensor, you have to pay royalty fees to use this process. Salaries for your employees, R&D, continuous improvement, all those kind of things. Apart from this, every year you need to pay profit for your shareholders, right? Interest payment, all those kind of things. So basically we separated total costs before production, before you start production, and once you start producing your product and start selling it. So after production you have, let's say, some negative cash flow, some positive cash flow, right? But before production you only have negative cash flow. So briefly speaking, we can say, yes, unfortunately I cannot read, but yeah, it is visible. Visible? So roughly speaking, it's all your cost plus profit. End of the day, so your total cost plus profit, your sales price or lot of costs. So cost can be fixed or variable. operating cost, what we are talking about, operating cost. So for an example, you are producing at certain rate and your variable cost would be cost of your raw material, right? But let's assume...
So second chart, that is...
I think it's just a copy of the other one by mistake.
Okay.
It's, wanted to show something else, but yeah, thanks for pointing out. So the operating cost can be variable, as I said, raw material, but there could be operating cost which is fixed. For example, you said lighting, lights for your plant, ventilation system, air conditions in your administrative buildings, right? Salaries for your employees, no matter if you are producing or not, doesn't matter. You have to pay salaries. So those are all variable operating costs, but fixed operating costs, right? And fixed cost, operating costs can also be direct or indirect. So directly related to your production, indirectly like insurance premiums and all those kind of things. So as we saw earlier, production cost is sum of your capex and opex, right? You have basically two phases, engineering and construction. So you engineer your plant, you construct it, right? And in between engineering and construction comes also P part, which is procurement. So you have to engineer it, and then you know exactly what you want to buy, right? You go and buy it, and then you go and construct it, and after that you start your operation, right? So that's, as we said, this is the phase where you really have positive cash flow coming in. Before that, you only have negative cash flow. Right? So let's continue with the same example. Everybody knows the molecular weight 28, 4 and 32 for these three components, right? So if you do the mathematics, you know, for example, I provided here the price of CO, price of hydrogen, which is specified here, right? And if you have to calculate the price of methanol, right, you can simply do mathematics or stoichiometric calculation and calculate based on these two individual prices, right, which I have also shown here, right? Turns out to be 0.225 euro per kg, somewhere around 225 euros per ton, right? If you go on internet and see, methanol is trading somewhere around 300 to 400 euro per ton nowadays. Let's take 350. So you already see you can buy methanol in market at 350 euro per ton. So that's the product cost, and you already see based on this stoichiometry, this is your variable operating cost, right? And the difference here between 350 and 225 is all the cost for your plant, for your salary, for your all other indirect expenses, right? So when you are in a very early stage or conceptual stage, you need to estimate your product cost, and you can come up with a business model or business case, right? So your estimation must be as accurate as possible, but you could imagine during the conceptual stage, what we saw in last 2-3 days, all what you have is block flow diagram, one sheet of paper. So for estimation of cost, capex or anything else, you apply several factors, and these factors are established based on years of experience and previous experience and knowledge, right? So let's forget 350 for now and continue with the very first thing, which is based on the stoichiometry and the reference CO and hydrogen price. This 225 we estimated, right? And we say, let's assume 10% of raw material is my other utility cost. So cooling water, electricity, all other cost is 10% of my my variable feedstock cost, right? So if I say this, then my total OPEX becomes 250, right? Now this assumption, this 10%, this may be good, maybe bad, huh? and this 10% will not fit for all kind of processes. So there could be some process where raw material cost is not so much, but electricity cost is the main cost. From last 3 days, can you remember what 2 examples? We had these 2 examples. Sorry?
Raw material as a fuel.
Yeah, the raw material cost was your major cost, but we also saw another example where electricity cost was your major cost or the only cost. So the 2 examples we saw, one was power production using natural gas. There your natural gas raw material cost was major cost, but then from solar PV, actually you do not have any raw material. So only cost was your electricity. Yeah, so your utility. So this 10 can be 2 or 3 for some plants or some processes, and it can be 95-99%. So you need to know which process you are talking about or you are estimating, and what suitable factor you need to apply, right? Now
the processing of raw material in purification stage, that is also included in the 10% or not?
Which one?
This 10% of raw material, maybe good or may not be good.
One second.
So let's say, for example, suppose if you have a raw material which is along with impurities.
Yeah.
So for the separation of impurities, we need to process the raw material. So that 10%.
That's all. That's
Okay.
Electricity and everything required for purification of your raw material. That's also included here. But as you said, this example is that you receive carbon monoxide and hydrogen in pure form. But just in case, if you receive it in impure form, right? With the same price tag, but your CO and H2 is only 90% pure, then probably 10% is not enough. So actually your 225 is already becoming 245, 10% more, because for the same price you are getting only 90% CO and 90% H2. So the 10% was specifically when your raw material is pure. Right? But this 10% will increase based on these scenarios. Your raw material is not pure, you have to use a lot of electricity or anything else to make the raw material pure, right? So that's what we said here. This 25, this can be 20, we assumed it, but when you do the real engineering, you start looking into details. As we said, we go from conceptual stage to basic engineering stage, and then you found suddenly, no, I don't need 25, I need 30. So there is whenever you make such assumptions, there is always an accuracy associated with this. When you say it's 10%, but it's with a plus minus 20% accuracy, that means I already know in my mind that this 250 can be 255 or it can be 245, right? Already you could see, you could calculate back this plus minus 2%, so plus minus 20% only on this, that means plus minus 2% on this. Already said the number, 255, 245, which is 2% of 5 is 2% of 250, right? Yeah, conceptual design, accuracy is plus minus. So you can say accuracy, but you can also see it as percentage error. Conceptual phase, when you have only one piece of paper with log flows, you do not have a lot of engineering definition, what equipments you need, what safety system you need. Your accuracy is very low, or let's say the error is high, plus minus error is high. But as you go in your project life cycle, you start putting in efforts, you define more and more things, your accuracy becomes better and better, so that percentage error reduces. Why we say risk here? So before lunch we talked about risk in different terms. process risk, safety, health, all those kind of risk. But there is also a financial risk. So in this session we are talking about financial risk. So there is no safety or hazard here. The risk is you lose money, you make loss. Risk is you are out of business. So that's all those things are financial risk. We talk this one. So you put in more efforts, you define risk as well as possible. With this, what we are doing, we are reducing the financial risk. So percentage plus minus error was here, let's say plus minus 70%. What it means in very early stage of project, you thought I will produce this mobile for 50,000 rupees because you know I need component A, B, C, and you said another 20,000 for things which I don't know now. But you started digging deeper and understanding how you add component A and B. Suddenly you realize, oh, I need component D as well, which costs not 20,000 but 30,000. Right? So this assumption in the starting that I need for other things which I don't know yet will cost me 20,000 can go wrong drastically. And with each and every step, you go out and understand, now I need to connect A and B, a D component, it will cost this. So what you are doing is defining it more and more, and with this uncertainty that you will have a surprise that I assume 20,000 but it costs 40,000. Your probability of this surprise you are reducing slowly, and which in turn means financial risk. So now let's go to the equipment cost. There are different ways of estimating equipment cost. Let's say we set the capacity of methanol production, which is basis 1,000 tons per day, right? And you know the space velocity or the specific volume of reactor required for this production, right? You can calculate back volume of reactor. So there are different ways. You can simply go out in the market and tell somebody or ask somebody, or specifically people who build such equipment, that I want a reactor with this capacity, please give me the price. And he will tell you, come back in 2 weeks, I will estimate. And then you say, okay, but before you leave, he says, give me 10,000 rupees even for estimating it. So everything has pros and cons. You can go out and pay something and get a better estimate, but what you can do also, you can do some calculation yourself. So you calculate it based on specific volume, means volume required per unit of fluoride. Calculate your volume based on the pressure, operating pressure. You can already know or calculate what's the thickness required. You know material of construction, thickness times area will give you the weight, right? You know the price of steel, you can already calculate your price. But you know, you don't buy reactors kilo ke bhav. You don't buy them at the rate of steel, because your fabricator or the company who is building this reactor, they will buy steel on per kg or per ton basis, right? Ingots, plates, whatever. But they have to do a lot of processing. They have to cut it, they have to weld, they have to put nozzles. So there are a lot of things goes into this, right? So one way is, as we said, you go out in the market, ask for a quote, which will cost you time and money, or you spend your own knowledge. Once again, factor approach. So generally at very early stage, it's a good practice to use factors and estimate your reactor cost or equipment cost, right? You don't know anything now, that how many nozzles you need, what will be the weight of how many legs you need, supports you need, all those details you don't know. But just calculating the volume, just calculating the weight, you can calculate, and you apply a factor, for an example 15, that gives you 374,000 euros in this example, right? But as you go into further details, then you know I will need four legs here. That's the height. So you add on weight of this one. So as you go along and increase your definition, have more and more details, your accuracy will improve because your uncertainties are going down. So what are the missing uncertainty in this, or what is 15, factor 15, because it's huge cost. You could think about, you could try to apply this for a car. What is the cost of a car, a decent car? It can be gross, but for a decent car, 10 lakhs, 8 to 9 lakhs. For simplicity, round figure 10 lakhs. And what do you think is the weight of car?
1,000 kg.
How much? 1,000 kg. Yeah, 1,100, 1.1 tons. So let's once again, for simplicity, 1,000 kg. And what's the price of?
10
sorry.
10 lakh.
No, price of car is 10 lakh. But now we apply the same methodology with this factor approach to end up with the price of the car. So 1,000 kg is the weight of the car, right? Let's assume everything is steel. Forget about all this, plastics, fiber, rubber, tires, and all this. Assume everything is steel or iron. What's the price of iron? Do you remember?
80 rupees per kg.
How much? 80 rupees per kg. Multiply 80 by 1,000. 80,000. Divide 10 lakh by 80,000. Sorry? Divide 10 lakh by 80,000. 12.5. And that's the factor what we have here. So either you can estimate price of a car with this factor approach, or you can go out and asking for price of car will not cost you anything apart from phone call, no money. But try to show the analogy between car price and so. But once again, this factor 15 can be different for different industry. We just saw for car it's 12.5. For something else it can be. If you try to apply the same factor or same approach for semiconductors, this factor can be up to 1. So there the price of metal is almost 1% of your total cost. You go and buy a chip, it will cost you a good chip, or a major chip will cost you, I don't know, half of a car, but metal is only 200 gram, maybe 1 kg. So this factor can be 100, 10,000. So as I said, it can be different for different product, different application. Right? So in this example, in our chemical industry, what are some few things which we could forget or represent this factor 15? Connected piping. You need to connect this to different equipment, this to the downstream equipment. So connected piping, different nozzles, piping for your cooling water, insulation if temperature is high or low. Insulation will be for both things, cold or warm, whatever. Then fabrication. He will go and buy pieces of metal, and then he has to bend it, he has to weld it, give it the shape of a reactor. So all those fabrication costs, all these things comes into this one. Right? So we said we have, let's say, 374,000 euro for this reactor.
कुछ गेम चेंजर्स का क्या है?
Cool. Thanks. So let's march forward. We had raw material for other raw materials or utility, right? So that was our OPEX. Now we added the CAPEX to price. But yesterday we saw, we had a simple block flow diagram of this hydrogen manufacturing plant, and then we saw a real PFD or real PFD. So reactor is not the only part of your plant. You have reactor, then you have integration, heat recovery unit, you have a separation unit, you have other utilities, everything. You don't know how many equipments you will have finally. So once again, you apply some factor. Let's take for now factor 100. So that will give you, let's say, your total capex. Right? So somewhere around 37.4. Now once again, is another factor. Whenever you use this factor approach, you are estimating something with some uncertainty. And when you have some uncertainties or something based on assumption, you will always have a percentage error. And that accuracy is defined by what's the plus minus value, right? So this is a very crude way of calculating total capex. That's why your percentage error is very high, plus minus. Your accuracy is plus minus 100%. So this 337 million euro can be 18 million euro, or it can also be 74 million euro. So all what we added up in these factors are your piping, all the instrumentation, safety system, civil road. So during the conceptual stage, there is no PFD, there are no PNID, there are no other documents available. You cannot do HAZOP. You don't know, as we were saying, how good what's the cell level of your safety system will be. So you have no idea, absolutely blind on all these costs. Right? So all those costs are let's say in very early stage included here in this factor. Now how we combine capex and opex, right? So two things. The plant you buy always has a life, like everything else. Car you buy has a life, maybe 10 years, 15 years, 20 years. So each product has a lifetime, right? So that means money you spend, for example, this 37 million euro probably comes to value of this plant will become zero at certain time, right? And that's called plant life. So generally we say 15 years, 20 years, that's the maximum you can have this plant life. Because beyond this, you still operate the plant, but you need to keep investing for repairs and maintenance and all other things that you can consider the value of your plant is zero in 15 years, right? So how do we convert, as we already said, we cannot add capex and opex to come up to the total product cost, right? So how do we convert our million euros, because capex is absolute number, million euros, and our opex is euros per ton or euros per hour. It's never euro, it's either specific to your product or specific to time, which both can relate via production rate. Right? So as we said, there are two things. One is depreciation. That's the rate at which your plant is depreciating, and 15 years is something what we consider your plant value becomes zero. Right? So that means your yearly capex cost will be somewhere around 2.5 million euros per year, right? So 37 divided by 5. And then there are several methods of accounting depreciation, because you buy a car, 10 lakh, let's say. If you want to sell it after 1 year, you get only 6 lakh. After 2 years, maybe 5 lakhs. So depreciation is also not linear. You will not depreciate, the value will not degrade linearly, same as every year. But in the initial years, it will degrade or depreciate faster, and then in later years, it's a little bit slower. Right? So if we convert, you remember our production rate was 1,000 tons per day, right? We have we said our depreciation or the capital cost is 2.5 million euros per year. Which is coming from 37 divided by 15, right? So 2.5 10 to the power 6 per million divided 365 for tons per day. That gives us 6.8 euros per ton. So now we converted our capex from euros to euros per ton, right? So that's about the cost of your plant. But who will give you 37 million euro for free? Apart from your parents. So that means you have to pay some interest rate. So you could finance your plant either from your own pocket, or you can go and get some loan credit from bank. So if it's a finance from outside or debt, you have to pay interest rate. And if it's equity or internal finance, you still have to pay something. The only thing is the name is different. It's return on investment. So I have my own money, but I also want my money to grow. I don't want my 37 million euro to be 37 million euro in 10 years. Right? So if it's from outside, you have to pay interest. But if it's internal financing, then return on investment, what you have to pay for your stakeholders and shareholders. So let's assume 10% interest rate, not so bad. We are in India, especially 10-11% for green projects. For some special projects, maybe lower, but generally 10-11% is what you have to pay. So similarly, we go 37 million euro times 10%, 10 to the power 6, same calculation. So 6.8 I have to pay for my plant. 10.2 I have to pay for every ton of methanol for our cost of capital, either internal or external. So that all together becomes 17. But then there are some hidden costs. Whenever you go to bank, they give you a fake card, don't tell you the hidden costs. So there are always some hidden costs here and there. So let's put some contingencies, 50%. With this, we already end up with this 17 and with this 8, so 275. So that's our variable costs. So those were operating costs, variable operating costs. Those are fixed operating costs. You produce your methanol or not, no matter, you have to pay. Bank will not listen. My plant was down for 6 months. So I will pay you only 5% interest this year. Now they want their 10%. So yeah, fixed and variable operating costs now become 375. And let's say you are targeting 15% profit. We are already at 360. You remember the number what we saw from internal, 350. But it's coming close now. So either that means if somebody is selling methanol at 350 euro per ton, is a greedy person, is expecting more than 15% profit. But if we are, let's say, generous and reasonable, with 15% profit, we can make business in market with 316 euro per ton. So how accuracy can affect your business case, or your profits? So you could see. So two scenarios. We keep the selling price same, 316. Right? That was the other variable cost for utilities. We assume 10%, right? And the accuracy was plus minus 20%. Suddenly this 25, after spending few months on calculations and doing all the engineering work, we realized it's not 25, it's 30, right? What was this 17? The plant cost, the capex, yeah. So we estimated the total capex 37.4 million, but in reality it's not 37.4, it's 74, double. So that's why the capex element is also double, right? And we also have to pay more on the contingency. So 8 was contingencies, right? Yeah, 50% of this. So once again, 50% of this. So all these things we thought will be this, but in reality turned up to be this. That means if I want to sell at the same price, I will have much lower profit. So I'm making only 11 instead of 41. Earlier we targeted 15% profit, but our wrong estimation can result into finally getting only how much it is, 3%. So that's why it's very important to have to apply correct factors and do your estimation properly at early stage. You cannot do in the early stage a lot of calculations so that you have accurate estimation, but you need to balance uncertainty with some factors, with some contingency, with some plus minus accuracies. So what we saw so far, OPEX, CAPEX, how we combine them, cost estimation, how we do it at very early stage, accuracy versus risk. That's what we saw in these two lines. If we are not accurate, we end up having a risk of earning less profit. And in the last few minutes, I also explained how you do not have enough definition or detail in the early stages, so you cannot make a good estimation. But you understand your financial risk. You understand if I have plus minus 100% accuracy, I have this risk of having only 3%. So you quantify your risk, you understand your risk, and you properly manage by already adding some margins here. So to do a good estimation, it's very important to have a very good sound definition. What is to be included, what is not to be included. You use database. As we said, for this reactor, either we can do, I said 2 ways, but there is another way. There are also databases available where you can pick similar equipment, similar plant, similar system, and take out the estimation and update it or scale it for your application. Right? So the companies who do such things now then or frequently, they have their in-house database. So for example, they bought 30 reactors of different size, different material, different configuration. In a department, they will keep all this information in a way that if they have to do estimation on one new reactor, they will take out 19 data points and simply calculate the best possible way for this new reactor. So this can also be in-house within the company, but that's only possible if you are doing this frequently. If you are doing this once in 5 years, it makes no economical sense to maintain such a database and department. Then, as I said, there are commercial database available. You get this to pay for the subscription, and then you can get all this information. Or the third one, what we discussed, you directly go to the supplier and ask for a real quote. Right? Now, elements of we estimated weight of the metal, multiplied unit rate of metal, and we applied a factor 50, and we had this cost, right? From this one equipment, we applied another factor, and then we had the total installed cost or the EPC cost. I'll explain what exactly EPC is, but the total installed cost of the plant, right? What exactly is in this total installed cost, we can categorize in 3 different parts. First is engineering, procurement, and then construction. So procurement is directly related to buying the hardware, right? And engineering is associated with all the time spent, and time is nothing but money. So you have to pay salaries to engineers who do all those calculations. So engineering associated with all the efforts or time spent to come up to a specification which you can give it to somebody and say, this is what I want to buy. Right? So you need to, like you were doing this calculation, what is the molecular weight of CO, what's the molecular weight of hydrogen, how much I will need, what's the typical specific volume required, that's the volume of reactor I need, all those calculations what you need, that's all called engineering. So the total TIC is split into these three parts, normally called EPC, engineering, procurement and construction. And construction, as name implies, is you engineer it, right? You spend a lot of time understanding what needs to be bought, how it has to be constructed. So all those things are here, all the costs during this period is here, and then you go out and buy it, and once you bought it, you also have to connect it together, build it, construct it, and make it ready to start producing what you actually want to produce, right? So we saw in the starting this factored approach. So that's the very basic approach. And we said that your definition is minimum. You just have one reactor, two reactants coming in, one reactor going into the reactor, and one product coming out. You do not know how you are going to pump this CO and hydrogen in this reactor. You do not know how many control valves you need. You don't know how many safety valves you need. You do not have any definition, any detailed out process flow diagram or any other documents. So with the minimum engineering definition, you apply this factor approach, which is nothing but factors based on your assumption and your experience, right? Major advantage of this is, as you already saw, we did it in 1 hour, right? So in reality, you do it in few hours, few days, maybe a week or so for a much better estimation, right? So very quick, and as I said, only a few hours, few week maybe, time required, right? The disadvantage, before going to this point, go look at the disadvantage. It's less accurate because your definition is minimum, barely minimum, right? So that's why it's high risk. And whenever we talk about risk, in this hour, it's always financial risk, right? So your accuracy is low, uncertainty is high. That's why your financial risk is high. But if you do it intelligently with better appropriate factors, right, and adding contingency or some margins in your estimate, you can manage this risk also properly, right? So as I said, accuracy can be managed if proper contingency added. So one disadvantage we already discussed. Another one is surprise in subsequent phase would cost a lot. So suddenly you realize, as Dr. Kanti said, you thought you will get pure, you made your estimation based on pure CO, pure hydrogen, but suddenly you go out in market and say pure CO is only 80% pure, right? So now on top I have to install a plant, a separation system which makes my carbon monoxide pure. So surprises, if you found in a later stage, that can cost a lot, and maybe you have not calculated well with the contingency. So
one more thing, during the manufacturing process, let's say for example, some unit may be in maintenance period.
Yeah.
So for that that backup equipment, that cost will also be included in that.
Yes, good question. So yeah, that's also based on experience.
Because production cannot be shut down for that time period.
Yes. So it's always let's say a study called reliability and maintenance study, RAM study. So let's take an example here. If you have total capex was 37 million here, right? And out of which this reactor is 20 million, and there is a pump for 1,000 unit, only 1,000 unit, right? If something happens to reactor, you cannot produce methanol. If something happens to this pump, you cannot produce methanol. Right? So what I will do, instead of one pump, I will install two pumps. Right? So with this, my production outage because of failing pump, I eliminated by installing one pump only, another pump, like a spare pump. So there you have to weight it with the capex, but with every additional equipment, you are increasing your cost. So you have to make this analysis. So what I mean, you are not going to install a spare reactor, which costs 20 million, because if you do this, your plant cost will not be 37, but it will be 57. But you can install a spare pump which costs only 1,000. Then your plant cost is 37.4. It will go up to 37.41. So, but you increase your availability of plant in case of your pump failing. Another advantage is what he wanted to point out is that you can do with this. You can do regular maintenance on your pump. And if you do regular maintenance, chances of this pump failing reduces further. So having spare pump is very common, but having spare reactor is absolutely uncommon. Yeah. So it's always cost versus. Yeah, that answers your question, your comment, no? Okay, let's move from this step to this step. So here we had only this reactor, two reactors coming in, product coming out, right? And then just before lunch, we discussed that we installed a cooling system, we installed some PICs, right? And it's an exothermic reaction, so we thought about, we became suddenly intelligent, a little bit more intelligent, and said the hot reactant can heat up the feed, right? So feed, effluent heat exchanger, so some heat integration we did. That means you are putting in more efforts to make it more clearer, detailing it out. So with this, you are increasing your engineering definition. You are defining more and more equipments. And now we will not calculate the cost of this reactor only, but we'll calculate the cost of this exchanger, this air cooler, this vessel, all based on same approach. What's the weight of this exchanger times this factor. So with this, with each and every detail you are adding in, you are reducing the uncertainties, thereby increasing the accuracy. Right? So the next level would be, let's say, the basic engineering, where you already have all the major equipments identified and put it on your piece of paper, which was earlier only one reactor, but now I know I need a heat exchanger, another air cooler, vessel, right? So it's a little bit time consuming compared to the conceptual one, but it's still time saving compared to the detailed one. In detail, we'll see in the next slide. Once again, low engineering costs or low time spent or low efforts required compared to detailed one, but still higher than the conceptual one. And I'll not repeat this accuracy and financial risk once again. So as you detail out, in essence, as you detail out your engineering, you are increasing the accuracy and reducing your financial risk. So if you go to a bank, they will not. You can imagine if you go to a bank and say, I need 37 million euro to build a plant which will produce methanol with this piece of paper, probably God will throw you out. So they also need to know that you have done your homework. So their trust in your business case or business plan also depends on how much detail you have thought about already. So as you go along from conceptual to basic to detail, you are reducing your financial risk, and lower the financial risk, more trust the developers or people will have on you, and you will have your project financing achieved easily and smoothly. So that was the second one. And then we have the third one. Here you could see we started only with one reactor, two reactants, one product. But suddenly now we realize these are the two reactants. We need flow control valves to maintain the production schedule. We need safety system, pressure safety valve. We need this heat exchanger for heat integration. We need utility cooling. Methanol is in liquid phase, so vapor liquid will be separated. We need this separator. Unreacted reactants will be recycled back. Right? We will need a tank, a buffer tank, to store methanol, because methanol will transport probably by trucks, and you will tap your methanol or fill your trucks by this pump from the tank. So basically this is the detailed process flow diagram, process instrumentation diagram, everything. Right?
Sir, one more question.
Yeah.
What about scheduling? Means, let's say for example, we produce volatile material, ethanol, methanol, something like that, which is not corrosive, and how long it can be stored in a particular tank before means supplied to the customer.
Yeah.
So there is a scheduling kind of things.
Yes, of course. So that also you have to plan before designing. So you could imagine, very good question or comment. So what will be the size of this tank? What's the tank size? How we calculate the size of this tank? Right. So we designed the plant at 1,000 tons per day, right? And let's say all these trucks, the average trucks running on the road, they are like, I don't know, 20 tons, 20,000 liter. So 20 tons they can carry. So if we are producing 1,000 tons per day and we have to supply it to the market by trucks, you can calculate how many trucks you need. So 1,000 tons per day divided by 25. Let's say 25 ton is one truck, almost 40 trucks a day. So you have 40 trucks a day coming in and out of your plant for refilling and filling, right? And then you specify some basis. So in our calculations, always there is a basis, and then you say my basis is there is a strike of trucks for one day. It means for one day there won't be any truck coming in to pick up methanol. Means you are producing at 1,000 tons per day. That means 1,000 divided 24 is how much? 42 tons per hour. So every hour I am producing 42 tons methanol. And normally every hour I was expecting to have 1.6 or 2 trucks at least, but they are not picking it up. So what I do, either I shut down the plant, but might be possible that for such plants shutting it down will cost you 6-7 hours, but restarting it again costs you 6-7 hours. So truck has arrived, strike is finished, trucks are arriving, but they are standing, but you are not able to start the plant. So there also you have losses. So you say my basis is I take into account 1 day of strike for the trucks and say I need a capacity here that I continue production for 24 hours.
So there is a lot of algorithms required.
1,000 tons here stored in this tank. So that would be one basis. Yes, you were saying.
There is a lot of algorithm is required.
Yes.
Means
yes.
how much we are producing and the number of trucks which is in queue
Yes.
to
Yes.
take the
So I try
products.
to explain that in a very simple way, but as you said, it's a complicated.
Is there any role of
calculation.
data science engineer over there?
Yes, of course, of course,
Or
of course. Okay, so once we move from only this on our piece of paper to this much detail, so you could already see hundreds of elements added, all the pipes, all the walls, the pressure sensor, temperature sensor, all the instrumentation, all the equipment, everything is added. So at this level, you already define major piping. You come up to this level that you know it's 1,000 tons or 42 tons per hour methanol is flowing in this pipe. I know velocity of methanol, I set it at 2 meter per second. With this I can calculate diameter of pipe, you know, like going from here to here is somewhere around 50 meter. So I can already calculate once again the diameter of pipe times thickness gives me the total area times thickness gives me weight of pipe, material, cost factor again. So again you add in all the required elements. At this level you already define major piping, all the instrumentation, safety system, all operation scenarios. Like you mentioned, there could be a scenario where you do not have off-takers, which are trucks, so everything going into the tanks. So probably there are some piping bypassing, you need additional piping. So all those scenarios you have to think about and install the equipment. Advantage, once again, very high accuracy because you have defined almost everything. There's a very small or slight chance that you forget anything. So accuracy is very high. The more you define, the more you identify risks. Right? So all the processes at this level are already defined, identified. Right? It's actually not a disadvantage, but yes, compared to the other concept and basic, it costs a lot of time. You could imagine. To me, to draw this costed 3 hours. So the first one, conceptual, I draw that, treat that in 10 minutes. So it's process one reactor. But to do this in Visio, it was 3 hours. So in terms of estimation, a lot of time is required for all these estimations, right? So basically, hardly ever you do this level yourself as a plant operator or as a client. You always have to outsource because for this effort, generally speaking, you need 6-7 months for a real methanol plant. 6-7 months, 70 people working full time, 40 hours. So you could imagine what kind of effort you need to perform this level of estimation, right? So hardly you ever do it yourself. You always outsource it. It's very tight schedule work. It's very difficult to manage. The more people, more difficulty in managing. Right? So that's what we talked about now in last 10-15 minutes. Conceptual, basic, detail. In terms of times, so a conceptual one can take few hours to few months. The basic one can cost you 4 to 16 months. Some 5 to 10 people working on it. But detailed one can cost you, 16 to 20 months. And as I said, maybe 70 people working at one point, peak time. So we move from a factor-based approach slowly to finally coming to real offers from the actual supply. So at this point, we start from here, our factored approach. At this point, we supply the EPC cost based on real offers with guarantee from vendors or suppliers that he gives me offer that I will supply this reactor for 37 million euro, and this offer is valid for next 6 months or something like this. So that means we remove all the uncertainties because we are now sure somebody has signed and guaranteed that I will supply this reactor for 37 million euro. So now this cannot be 37 to 37.1 actually if you order it within 6 months. So the sole purpose going from here to here is to remove all the uncertainties step by step so that you have very high accuracy on your final estimation. So procurement cost of equipment or all the hardware that we already talked about. Maybe quickly touching upon what exactly is included. So major equipment, reactor, heat exchanger, all those things. Bulk, we call normally all the piping. Piping means piping support and all other piping elements, right? So Apart from pipes, all kind of walls, all kind of non-consumables. So we categorize in between consumables and non-consumables. So with the name you could understand. Consumables are reactant A and B. But if you have catalyst in your reactor, that's not consumed. It's just sitting there. Still, you have to pay for it. It's quite expensive. So bulk civil, such as ladders, platform. On the columns you have ladders and climb and go and do maintenance. You need spares for next 2-3 years, which can be, as we were discussing, pump. It can be a installed spare, installed in the plant, and with the automatic system, if one fails, other ones will start automatically. Or it can also be a warehouse spare. Means you don't install it. That means you don't have to pay for each and everything, but you just keep impeller, because you know in a pump what fails impeller. Instead of installing everything there, I just buy a impeller for next 3-4 years, leave it in my Almira, and if it fails, I quickly go to my office in the impeller house and start the plant again. You have to balance. You want to pay for the whole system with this automatic system, or you say, okay, instead of calling the vendor and waiting for 3-4 days that he send me the impeller, I put it in my Almira, pay a very small amount. With this, I save my 2 days or 3 days. It's always you have to think about what is the best possible. So then all other instrumentation here is here in this P part. So far we saw a bottom-up approach. Means you say, I have equipment, that's my weight, that's my factor, and slowly I go up and then say, that's my 37.4 million total capex of the plant. That's bottom-up approach. And there is another one, top-down. You say, I apply factors now. So for an example, if my equipment cost is 100%, or let's say 100. And you can say your piping and utility, that's somewhere around 30 to 34. That's typical for chemical plants, but it can be a little higher for power plant, because you have a lot of piping, a lot of water going here and there, steam system here and there. So bulk piping elements like orifice, bends, reducers. You have a 6-inch pipe, and then you have to reduce it to 4-inch pipe, so reducer. All these are called piping elements, so that's also significant part, 5 to 10%. Instrumentation control, add another 20%. Other things, insulation, whatever, 5-10%. So I say if I have 100 million for the buying the major equipment, I will have somewhere around 180 million total procurement cost, total cost of the plant. Only buying. Right? So you saw we went from here to here. What will allow us? So when we were here, we only had major equipments, and we could apply this method and end up here. As a next step, what we can do, we put in all the piping, all the instrumentation, everything, and actually calculate what this will be: 30, 33, 35, 40, 41. Yes, I think we can skip. Then the major cost normally what you think is cost of equipment, but in chemical plant the major cost is associated with construction. It's also was surprising for me in early years. I thought what is standing there more often than not, you buy something for 100 and to get it installed, and before you see you already spend 300. So construction cost is this phase is also the longest phase of your total project life cycle before you start the production. So you do conceptual design in 2 weeks, 2 months maybe, basic engineering in less than a year. You do detail engineering in maybe 2 years, somewhere around 3 years, 2.5 years. But in this detailed design, you already have the construction start. And the biggest period is the construction. Sometimes it takes 2 years, 3 years to build your plant. You order it today, you will get the delivery after 1.5 years, maybe sometimes 2 years. So you have to start early. Greenfield, brownfield. I think Dr. Kalpana mentioned yesterday. Greenfield is field where grass was growing, was all clean, and suddenly you say, no, I remove the grass and put a permanent plant. So that's how the name came from, greenfield. And brown is where you already have installed something, so it's all it's brown. It's not green. So revamp. You want to make change in your plant. That's all about brown. So engineering you can do anywhere. We are sitting here in India, and we can ask a company in Germany or in US to do the engineering, right? But construction is very local because you need local know-how, local expertise to do your construction. So you have to engage with local companies. Sometimes some sort of engineering or calculations you can do in-house, but for sure construction never. It's very, very, very specific job. So hours spent in terms of hours, that's why also the cost is 10 times more than engineering hours. So doing the calculation cost you maybe 1 day, 2 day, 3 day, but really having this reactor engineered, built, fabricated, transported, installed, inspected, all those things, it will cost a lot of time. So we were, let's say, at 100 and 180, right? That was our P. So once we have, let's say, once we have E and P together, and we want to estimate the construction cost, once again it's the same approach. You apply factors 1.8 to 3, and this factor varies a lot. You could imagine you I don't know how to explain, but maybe this piece of plastic cost you only few rupees, but if installing this with this electrical system needs special know-how, you will have to hire a special worker for this, and he will charge you maybe 200 rupees. So your P price was only 10 rupees, but you have to pay 100 rupees to get it installed. So this construction part can be sometimes factor 10, but in chemical plants it's generally somewhere between 1.8 to 2.5. So example within the chemical plant could be a compressor, which generally is supplied as totally engineered on a skid. All what you have to do, they will send you the drawings and say, please prepare a cemented or a concrete structure of this length and width, and with 4 holes for the screws, and they will send you the whole system, and you just have to put 4 screws and you are done. So for such system, your factor would be even 1.1, because you barely have to pay anything for your construction apart from this structure or foundation, right? But for some equipments, they will send you only vessel, and then you yourself apply the insulation, cladding, many things you do yourself. People are standing, you have to scaffolding, you have to prepare scaffolding going up and up. And so sometimes for some equipments the cost for during the construction can be very high. But that's the general factor which we generally see within our chemical plants. Right? It can also depend heavily based on the location. You could imagine hourly rate. In India it could be 50 euro per hour, somewhere it could be 200 euros per hour. So your construction cost can be quite different. And it's not only hourly rate, but it's also productivity. What it means, the productivity, probably you understand this. Workers in India probably give you less productivity, more productivity compared to some other countries. So same amount of time, they will perform less work or more work. So some countries very high hourly rate, but also very high productivity. So end of the day, construction cost is lower. Right? So it's not only you look at the hourly rate, but you also have to look at the productivity. And if you go on internet, you will easily find the databases for productivity of different countries. Right? Another element of construction cost is cost associated with authority, dealing with local authorities. So labor laws can influence your construction costs heavily. For example, in European countries, truck drivers are not allowed to drive more than 6 hours a day. There are no restrictions as such in India. So transporting 10 tons from point A to point B might cost you much higher in those European countries. Not because this driver don't want to drive, but the law prohibits. And hiring another one, so it's not just hourly rate. You can say you hired another driver, but the salaries you pay is not only the hourly work they perform, but also some fixed amount. So cost is always higher. So what I want to say here is your construction cost can be heavily influenced by local labor laws. Economy of scale. So we want to design a plant with 1,000 tons per day. We know the specific volume, and where this specific volume is coming from, probably from some laboratory experiment. We know for 1 ton per day, we perform something, let's say in 1 ton per day capacity, and now we want to scale or estimate what could be the cost for 1,000 tons per day. So for example, we have this data point now for 100 tons per day is 374 billion euro. That's my material cost, that's my fixed cost. If I go from 1,000 to 500 tons per day, my fixed cost will remain same, right? Because fixed cost is something which is not linked to your capacity. Fixed cost is, you will have it in any case, like transportation, some other costs, and material cost will be, let's say, now I don't need 20 tons, I need only 10 tons, or other way around. So that's how you can calculate back your material cost. So cost for a reactor of this capacity is 374, cost for this capacity is 234. Right? And if you try to plot it, it comes out to be in a log let's say relation, and 0.6 to 0.65 is the factor what we use. So let's say that's the capacity at point A. The cost at point A. That's the capacity at point A or capacity A. That's the new capacity, and that's the cost you can calculate with this formula. Based on, so for example, we know this capacity, this cost. I want to know cost for this capacity. So that could be 374 times 500 divided by 1,000 to the power 0.6. So generally, in chemical plants is 0.6 to 0.65. It can be a bit higher, a bit lower. What you have to be careful is, if you start estimating the cost of this capacity from a capacity data point which is 10 or 20 times higher, then it's risky. So this method works well for closer capacity. Like if you know something, some data for 1,000, you can go for 500 or 1,500. But if you want to do something for 10, it's not a good idea. Or something like 10 to the power 6, it's also not a good idea. So this method works well for closer capacity, but not for very high. Okay, I think that's it for questions, comments, costs, money, questions, comments, views, right, wrong, anything you want to add.
What is